there's a line on the notes on page 18. I added 4 words, and it says the X alpha, it now says X alpha, which is the image of the chart pi alpha. It says X alpha is open in X. It's important to specify that X alpha be open. That is, the patches that come from charts are open. I hope I said that in class. If I didn't, that was a mistake, and I should have said X alpha has to be open inside of X.
Doesn't it come from the homomorphism of the chart? It
does not. So then that's yeah. I had to think about that for a second. But so if you have if you've got a space here X, and you've got some subset like this, right? Then the topology induced on this thing, the open sets are what you think they are. They're sort of the open intervals in here. But this subset is not open in X itself. So you can have a map from this to that, which is a homeomorphism onto its image, but its image is not open in X. So you have to specify specifically that this thing is already open itself. Yeah.
Like, if you just specify it's like a homeomorphism on all of X alpha, because right now if you just have, are those open intervals right there? Or?
Yeah, this is an open interval inside of R.
And is that an open interval, like the equivalent of open interval inside of X?
Well, it's not equal to it, but it's in bijection with it.
Okay.
You see what I mean? People online, can you guys hear me? Yes, you can. Okay. I was looking at Garrett kind of doing that. I'm still like, oh, wait a minute, can they not hear me? There's no other way to alert me, actually, except by waving if you can't hear me. Yeah, so this is supposed to be an open interval in R, and then its mapped to this thing is a homeomorphism onto its image. Its image is a topological subspace of X, and the open subsets inside of this image, inside of this arc, are just the sort of, the open sub-arcs, if you like, right? Which can be disconnected and so on. So like that's an open subset. But this thing is not open inside of X. So you have to specify that separately. You have to actually say that it's open. Yeah. And if I didn't say that in class, then that was entirely my fault and should have been specified. Yeah. The point is that a subset of X is open if and only if it's covered by the opens that come from intersecting with each patch. That's the idea. It's not supposed to be a complicated thing, but without this is open in X business, it's not possible to prove. Yeah. Further questions? Let's talk about orthogonal groups. So this is going to be different from what we've been doing. We're going back. So as this course does fairly frequently, it goes back to elementary, and then we'll start getting, sort of more abstract, and then we'll go back to elementary at some point again, and then we'll go abstract again. So this is in some sense a new unit, although we're going to use stuff that we've done. So this is orthogonal groups. And again, people online, you can read this. Yeah, good. So here's a question. What are the symmetries of the sphere S2 inside of R3? So this means the sphere, right? And symmetries, you should think of that as being you pick up the sphere and then you do something to it and then you put it back down. Technically, what that means is you're looking for a group that acts on the sphere in the way that we've defined group actions. In such a way that what? Well, how would I specify this? What do I mean by asymmetry of the sphere? I mean, for instance, if you think of the surface of the Earth as being sort of squishy, if I put my finger down and sort of stretch a little bit, then I still end up with a sphere. But that would be asymmetry of the sphere as, let's say, a differentiable manifold or something. But I want something more rigid than that. I want to think of the sphere as being a metric space. And then I have to tell you what an isometry is. So we defined metric space a long time ago. And I could have defined metric space on the very next line. This is an elementary definition that we just haven't used yet, but we could have defined it on day 2 or whatever it was. So this is an isometry of the metric space. is a bijection and the bijection, let's just write it as phi from x to x with, and then you have to specify that the distance between the images of 2 points is equal to the distance between the 2 original points. And that's for all x and y in the original metric space. It's what you think it is. That is, you're going to take x to itself and you're not going to change any of the distances. So in terms of the sphere, what is the distance on the sphere, by the way? What is the distance on the sphere? How would I think of that? I've got my pole there.
Isn't it parts of great circles?
Yes, it is. Otherwise known as angles. Right? So this is why we use radians. Right? So the distance between, say, this point and this point is, you look at the length of that arc. So the length of that arc, so if that's x and that's y, then that has the length, is the angle between x and y, thought of as points in R3. Right? The angle measured in radians. That's why we use radians, right? It's the arc length between 2 points on a circle. Yeah, so that's the distance. So that's d of x, y. So if I told you that you have, so an isometry is supposed to be a bijection. I claim it's enough to assert or prove, if you're given a situation where you need to prove something as an isometry, it's enough to prove that phi is a surjection.
No,
Yeah.
that's for the unit sphere, right?
Sorry, yeah, the units, yeah, the unit sphere. When I write S2, what I mean is the metric space that is the unit, that is the, how do I say, it's the metric space that is the unit sphere in R3. Now, by the way, I could have made it any sphere if I wanted by doing this. But the angle between 2 vectors is the angle between 2 vectors, no matter how long they are. So I could have made it any sphere. It's a unit sphere. You get the angle from the length if it's the unit sphere. But in general, I could have just said take any sphere, and then the angle between these two things is the angle between them, which is, log cosines business. Yeah. It would be enough to say that phi is surjective. If phi is surjective and it preserves distance, then it's automatically injective. Why is that? So, because note that is that you need only that phi maps x surjectively to x, since if you have x not equal to y, then what's the distance between phi of x and phi of y? Well, that's going to be the distance from x to y, which is not 0, because x is not equal to y, and this is a distance. This implies that phi of x is not equal to phi of y. Right? So it's automatically injective. That's the point, right? A function that preserves the distance between x and y preserves the fact that x is not equal to y. That's all I'm trying to say. It's a very simple statement. If these two things are different, then the distance between them is strictly positive. The distance between their images is therefore also strictly positive because it preserves distance. Can you give me an example of a metric space where you have a map from the metric space to itself that satisfies everything except for it being bijective? So everything except for surjectivity.
Can you repeat?
Yeah, fine. Let me write it down, actually. So let's find x, d, and phi satisfying all but surjectivity. So it's going to preserve distance. This is going to be a function from whatever x you choose to x. And it's going to preserve distance. It's going to keep points the same distance apart, but it's just not going to be surjective. Has to be injective because it preserves distance. Any ideas? Yeah, Ben?
It's a bad idea, but if you have a circle in R3 and you rotate it around, like maybe the z-axis or something, preserve distance,
But that wouldn't take the circle to itself. Remember, it has to be a map from X to X. So you were saying something and you made a little motion which made me happy.
I said +1, but
Yes, you said +1. Yes, okay, good. So +1, so what's the space? I like this +1 business.
Integers?
Say it again?
Let's take the integers.
Oh, the integers. Okay, so you're gonna take a map from Z to Z. Right? And you're gonna go from Z to Z, and then what are you gonna do?
Add 1 to it.
Okay, and this is gonna be by +1. That's bijective.
it is not surjective.
It is surjective.
Okay, then 0, 2.
Aha! So don't use Z, use N instead. And now it's not surjective. Right, so this is bijective, and this is injective, but it's not surjective. You could also, by the way, have used, instead of N, you could have used R greater than or equal to 0. And it feels more like a metric space. Right? And then this map is +1. Translation to the right. The translation to the right is injective, but it's not bijective if you have a left endpoint. That's the, okay. So here's a question. Is every isometry of S2 rotation about some axis?
No, because you can reflect. Well,
The answer that comes immediately from Nicole is no. It was Nicole, right? Yeah, sorry, people just behind me, I couldn't see. So the answer here is no reflection. How do you know that reflection is not rotation around some axis?
it's not orientation preserving.
Aha! So there's this notion of orientation. What is orientation? Yeah, it's fun, huh? What is so it isn't orientation preserving, that's right, but why not? It's the reason why you can't superimpose yourself on your mirror image.
does it have to do with vectors perpendicular to any point? If you rotate it, it's going to be the vector perpendicular to it's going to be differently oriented than if you reflect it.
Yes, more or less. Yeah, so it has to do with sort of looking at vectors that are orthogonal to one another and then seeing which direction things point. Let's make this precise. So the point now is that we need a notion of orientation. So let's get a notion of orientation. So, so first of all, let's just note some things. So if P is isometry of S2, then it preserves orthonormality. Of bases, right? Why is that? It's because it preserves angles, right? This is nothing else than it preserves angles. So if you have an isometry, then it preserves the angles between vectors. And so if you have an orthonormal basis, that means that they are unit vectors, which means that they lie on the sphere, and their angles are preserved, so they remain orthogonal to one another. Yeah? That's just by definition. Okay, let's define V1, V2, V3 to be right-handed if, and here's what more or less Ben was saying. So V1 cross V2 is equal to V3. So what's the picture here? The picture is that you have, that has to be V1, not has to be, that if that's V1 and that's V2, then V3 points up, right? So it's I mean, it's an orientation thing. There's sort of no way to say it without speaking three-dimensionally. If you go from V1 into V2 by an angle of pi over 2, then V3 is now pointing in the direction that's on the sort of positive side of that plane, whatever that means. But I could have drawn this picture upside down, and then would have been V1, V2, and then V3 points down. If I switched to V1 and V2, then V3 would point down. Yeah, so I was in physics class once in high school, and there was a substitute teacher for oh no, this wasn't the substitute teacher day. This was just a regular test. And people were doing, it was on the right-hand rule, you know, which way current flows and all this kind of stuff. And it was so funny. At some point, I sort of, you know, was thinking about a question, and I sort of picked my head up and kind of looked around the room a bit. And I saw all these people holding their pencils like this and doing the right-hand rule like this. And they were all getting it wrong by a sign, right? Because they were using their left hand to do the right-hand rules. And the whole point about it being the right-hand rules, you need to use your right hand. That's why it's called right-handed. So this is the usual axis. This is x cross y equals z is how you remember this, right? Yeah, okay. So that's right-handed. In Rn, we say positively oriented. If the determinant of V1 up through Vn is positive. And this actually doesn't require this to be an orthonormal basis. It really doesn't. You could make this V1 through Vn any basis of Rn. And you say it's positively oriented if the determinant is positive. You say it's negatively oriented if the determinant is negative. That's all. You notice that if you switch the sign of any single column, it's going to change the sign of this one. Yeah. And then we say that phi preserves orientation. If it preserves handedness. Okay. So examples. This is elementary, but how about Nicole's example, right? You said reflection. Yeah. So why does that not? So first of all, how would I write down reflection? What's a nice example of a reflection?
Arch negative R reflected the origin.
You said you reflected what?
You could reflect through the origin.
I could. What matrix would that be?
Just make every entry negative.
That's right.
Yeah.
Every entry of what?
On the diagonal.
Yes.
So the negative identity.
Yes, negative identity. Which is the first example I've written down. That's why I was pushing you to do that. Keep in mind that this is really reflection through a point, right? This is reflection through the origin rather than reflection through a plane. But it can also be expressed as reflection actually, can this be expressed as reflection through a plane? It can be expressed as rotation and reflection. So this has some reflection and rotation in it. So this is not just a reflection, actually. This is sort of a reflection and a rotation. Because if you reflect through the origin, then you have to sort of rotate back in order to put the V1 and the V2 where they started. Right? If you put this thing down there, and this thing back there, and this thing back there, then you can rotate it back. You can rotate it back to make it so that V1 is on V2, but then V3 will point down. That's the point. Yeah, so the point is if you reflect V1 and V2 back here, then you can rotate V1 and V2 back. So it's important that this is a 3 and not a 2, right? So how about, let's look at just, how about negative I2? How about this? Is this, in R2, is this oriented positively? Does this map have, is it positively oriented? Like, does it preserve orientation or not? Yeah, it preserves orientation because the determinant of minus I2 is what? Right, the determinant of minus I3 is -1. The determinant of minus I2 is 1. that means that minus I2 preserves orientation. What is minus I2? Minus I2, we just talked about it, but it takes this thing, right? It takes this thing to there, and it takes this thing to there. And so what it's done is it's just rotated by pi. So this, that's rotation by pi, which is orientation preserving. So the fact that we're talking about S2, which is inside of R3, and 3 is odd, the oddness of 3 is very important for this discussion. That's what I'm trying to tell you. Okay, so this is not. And then we've already said reflection through a plane as opposed to through a point. And this is also not orientation preserving, but if phi is rotation around a line, then it is orientation preserving. Okay. So if phi maps Sn minus 1 to Sn minus 1, if this is an isometry, you understand when I put Sn minus 1? This is, so S1 is contained in Rn. This is the set of unit vectors in Rn. Fair enough? This is called the unit sphere, the unit n minus 1 sphere. Why is it called n minus 1? It's because this is a manifold of dimension n minus 1. Right, now you know what that means. And that's going to come up again, of course, manifold. So this is an isometry that if you have an isometry of the sphere, then what you get, if I look at alpha times phi, such that alpha is a non-negative real number, then this is an isometry of Rn. What do I mean by that? So the point is that Rn is a union of spheres of various radius. This is that picture of just so you have a sphere to look at. So the point is here that Rn is the union over all alpha greater than or equal to 0 of alpha times Sn minus 1. This comes down to the frankly dumb statement that every vector has length alpha for some alpha. Right? This is the vectors of length exactly alpha. And it's just saying every vector has some length. So what I'm saying is that every isometry of the sphere extends to an isometry of the entire vector space. And the way I extend it is just to sort of copy the isometry at all positive scalars. Let's prove this. So if you have two vectors x1 and Rn, then I need to show that this thing is an isometry, right? All I'm really trying to do is prove that this set of functions from the various spheres to themselves, they induce an isometry from Rn to Rn. Yeah. So if I have two vectors x, y, and Rn, they needn't be of the same length, right? So they don't have to lie on the same they don't have to lie on the same scalar multiple of the sphere. But nonetheless, I can apply. So x has length alpha, so I apply alpha times phi to this one. And y has length beta, so I apply beta times phi to this one. Yeah. And then I get 2 points. So what I find here is that phi, what does phi preserve? Well, first of all, it preserves the length of x and the length of y. That's really by construction, right? Because each of these things, that just says which sphere you're on, and it doesn't change which sphere you're on. So that's by construction. It fixes the angle between x and y, and I'm going to define that to be the angle between x over the length of x and y over the length of y. That's going to be the definition. and that's by isometry of Sn minus 1. Clearly, I would want x and y both to be non-zero. If one of x and y is 0, then you can figure out what's going on here. I just don't want to mention that. Nothing bad goes on. And because of these two, this implies that it preserves the distance between x minus y, between x and y, and that's by the law of cosines. And that's the whole proof. Remember what the law of cosine says? Anyone remember what the law of cosine says? No?
A squared plus b squared minus c squared is equal to 2ab cosine c.
I think that's right, actually. So I remember it as a deformation of the Pythagorean theorem, right? It says a squared plus b squared equals c squared. That's true if there's a right angle, right? But if the angle across from the length c is not a right angle, then you have to modify it by adding 2ab cosine of c. Which I think is what you said if you just put the c squared on the other side. I think that's what you said.
I was tutoring one of the kids who was taking geometry, so.
Good to know you got it right. Okay, so then what would this be? This would be the length of x squared. This is the length of y squared. This is the length of x minus y squared, right? 2. And this is going to be 2 times the length of x times the length of y times, and now this is going to be the angle between x and y. And the point is that we have preserved, right? We've shown in the first 2 lines that you preserved this term, and that term, and that term, and that term, and that term. And there's only 1 term left. Therefore, it's preserved as well. What this means is that if we want to talk about isometries of the sphere, we may as well just talk about isometries of Rn, which somehow feels more linear, right? We were talking about spheres before, now we're talking about isometries of a vector space. Okay, so here's the theorem. That is that every isometry of Rn has the form it has the form A plus T sub V or some. Okay, where A is a matrix that is orthogonal O(n) of R. What is that? That's the matrices Q n by n, such that Q inverse is equal to Q transpose. That's called the orthogonal group, which is quite unfortunate. It should be called the orthonormal group, right? Because the matrix, the columns of this matrix are orthonormal. They're not just orthogonal, but they're orthonormal. That's what it means. But it's called the orthogonal group, and there it is. It would be denoted by an O anyway, so there you go. And TV is translation. This is translation by some vector V in R. That is, every isometry is multiplication by some orthogonal matrix, and then you add that to a translation. Fair enough? Translations certainly preserve distance, right? Orthogonal matrices preserve distance, more or less because of this, but they, just by definition, but they preserve angles. Okay, so let's prove this. Let's assume that phi is an isometry of Rn. Okay, every isometry is a map from Rn to itself, and so it takes 0 somewhere. phi of 0 is going to be some vector v. Now I'd like it to be 0, right? So how do I make it 0 while still preserving this kind of thing? So I have some transformation. It's going to pick up Rn. It's going to do something to it. When it does that, it happens to move 0 to v. I would like to show that phi is the sum of an orthogonal matrix and a translation. How would I do that? Well, I'd like to say that if phi didn't move 0, then it was an orthogonal matrix. So what I'm going to do is subtract off the translation that takes v 0 to v, right? So let's replace phi with phi minus t sub v. Right? So if I prove the result for phi minus t sub v, it's still true. Right? If phi minus t sub v is the sum of an orthogonal matrix and a translation, then phi itself is the sum of an orthogonal matrix and a translation. You have to note that tv plus tw is t sub v plus w. And if I translate by v and then I translate by w, it's the same as translating by v plus w. That's all we're saying. Not a big deal. Okay, so now what I need is that now phi, or it's certainly enough, is that now phi is orthogonal. So the proof is as in the lemma. It's essentially the same thing, but you need one more thing, which is that you need to know that a length-preserving map from Rn to itself is linear. So plus length-preserving implies linear, or plus preserved inner product. Implies linear. So what you need to do is you need to show that phi, if it's an isometry, then it's supposed to be a linear map that preserves inner products. That's what it means to be an orthogonal matrix. It's a linear map that preserves inner products. And so the first thing you need is that if it's an isometry, that it preserves inner products. And that is more or less what this thing does. It's an argument very much like this. And then you need to say that, okay, well, that means it preserves inner products, but is it linear? Right? It's not obvious a priori that a map that preserves inner products is actually linear, but it's not hard to show. Why is that, by the way? Why does preserving inner products imply linearity? Well, it's more or less that ax, if you look at the ith coordinate, what is that? That's just ax inner product with I. So the coordinates of your map just come from applying inner products, but inner products are preserved because it's an isometry. Yeah, so what you need is you need to prove that isometry implies preserving inner products, and that preserving inner products implies linear. And as I say, isometry implies preserving inner products. That's more or less what this argument looks like. And then the rest is just basically this. Right, so this is a fundamental fact that you should carry with you sort of for the rest of your life. It's a simple statement, but every isometry of Rn is an orthogonal matrix plus a translation. Very useful, yeah.
Does the theorem extend to Cn, like complex?
We're going to talk about Cn shortly, maybe next lecture. We'll talk about unitary matrices. So we're going to talk about, so we will talk about, I'm not sure if we're actually going to prove an analog of this exact statement, but we will talk about unitary matrices next lecture, or maybe the very end of this one. We'll start talking about it. We'll talk about a lot of it next lecture. Okay. Let's see. So what do we need? So let's see. What were we talking about? We were talking about isometries of Sn or S2, right? And then we ended up talking about isometries of Rn. So let's just think about this. Since we were interested in the isometries of Sn minus 1 to begin with, yeah, what kind of isometries of Rn give me isometries of Sn minus 1? Remember, every isometry of Sn minus 1 extends to an isometry of Rn. That's what this statement says, right? So if I had an isometry of Sn minus 1, what kind of matrix, what kind of transformation would I get up here? What can you tell me about it?
Well, you can't translate it because then it would shift S1.
Right, V has to be 0. So it says the TV part is actually 0. So the note here, the note is that Sn minus 1, what is that? That's x in Rn such that the length of x is equal to 1. That's fixed by an isometry phi of Rn. And that's going to be if and only if phi of 0 is 0. All right, so we're looking for the isometries of Rn that fix 0, otherwise known as orthogonal transformations. Corollary, that is that isometries of Sn minus 1, those are in bijection with orthogonal matrices. Good.
So I understand this part, but where did the translation moment where did it come into the proof of the lemma? Like,
So which lemma?
like in the proof on the left side of the board?
It doesn't. And the reason why it doesn't is because you started off with the transformation of an isometry of Sn minus 1. And our conclusion here is that when you have an isometry of Sn minus 1, the only kind of thing you can get is an orthogonal matrix. There is no translation of that.
So how can we use the lemma for the proof, for the theorem, if we do not assume that?
The lemma is not part of the proof of the theorem. It is just a statement in its own right. The lemma was just a simple statement to prove that reduces, so the corollary, this is a corollary of the theorem, but the corollary uses the lemma. The lemma is going into proving the corollary, not the theorem. Right? In particular, the corollary, so the lemma is this way. That's the lemma. The lemma says that the isometries of Sn minus 1 map to the orthogonal matrices. It actually says that the isometries of Sn minus 1 map to all isometries of Rn, but then this note says that the image is actually the ones that fix the origin. So we have our question that we want to answer, right? We want to answer what are all the isometries of Sn minus 1. So let's think about this for a second. Oh, sorry, of S2. So this is the answer to our original question. So if you have a matrix A in O3, the question, remember, was, is every isometry of S2 a rotation about some axis? And the answer is no, it has to preserve orientation. So if it preserves orientation, is it rotation about some axis? Right? We know that it's given by a matrix in O3, and that matrix has to have determinant 1. But okay, what does that mean about the geometry of it? Is it a rotation around some axis or not? So let's try to figure that out. So if you have A in O3, an orthogonal matrix, then the A has a real eigenvalue. Why is that?
Because complex eigenvalues come in pairs.
Because complex eigenvalues come in pairs. Why don't you give me the even shortened version of that statement? Because 3 is odd. Right, I told you that would be essential. 3 is odd. So if any matrix that's n by n, where n is odd, has to have at least one real eigenvalue. Because any real polynomial of odd degree has to go from negative infinity to positive infinity, or positive infinity to negative infinity. So it has to have a root somewhere in between. Okay, so this is 3 is odd. Very good. So it has a real eigenvalue. What can you tell me about that real eigenvalue? Well, at least one of them is plus or minus 1. Lambda is plus or minus 1. That's it is. At least one eigenvalue is lambda equals plus or minus 1. Why is that? Well, I think the absolute value is 1. This is a homework problem, which I don't know if I already assigned or whether it will be in homework 3, which will be after the midterm. But it's not supposed to be hard. Orthogonal matrices, their eigenvalues all have absolute value 1. Okay, so this implies that there's an eigenline, right? If one of the eigenvalues is plus or minus 1, that means that there is an eigenline. And that means that eigenline, this is the axis fixed, and I'll say pointwise, that if every point on the axis is fixed by either A or minus A, and this is again because n is odd. No, actually you don't need n is odd for that. Right? If you have an eigenvector of eigenvalue minus 1, then minus A does A and then minus 1, and so that fixes the line pointwise. Right? If the eigenvalue is minus 1, then it flips the line. But then if you take minus A, it flips the line back again. Okay, so this doesn't use odd or even. Okay, one of these preserves orientation. One of these preserves orientation. Okay, but A is an orthogonal matrix of size 3. This implies that A takes an orthonormal basis to an orthonormal basis. It preserves orthonormality, right? Oh, I suppose I can write it that way. Takes an orthonormal basis to an orthonormal basis. No, I need to, I'll leave more room. So it takes an orthonormal basis to an orthonormal basis. This means that A restricted to P, orthonormal basis, this is of P, which is going to be the line perp. Right, so we have this axis, we call that axis, right? There's an eigenline as an axis. Now let me look at the orthogonal space to that axis. So really, there's a line in R3, right? And there's an orthogonal plane to that. And we have our orthogonal transformation A, and it takes the line to the line. So it has to take the plane to the plane. And furthermore, it takes any orthogonal basis in that plane to another orthogonal basis of that plane. Fair enough? Okay. So that means that A restricted to P is rotation of P, and then possibly followed by a reflection of P. Right? So if you think about what orthogonal transformations of the plane look like, now you're just taking pairs of vectors that look like this, right? So we're literally just talking about pairs of vectors that are orthogonal to one another in the plane. And you want to preserve the angle so you can rotate or you can flip. And that's all you can do. So that's, I suppose, a lemma that you have to prove that we might have actually proved in 221, but I don't remember. In any case, it's possibly followed by reflection. But I claim that this can't happen if it preserves orientation. Why not? So here's a proof of this. So suppose that E1, E2, E3 map under A to V1, V2, and V3. Okay? So this is supposed to be orthogonal. So A is supposed to be an orthogonal matrix, size 3. So what can you tell me about the determinant of A? The determinant of A is V1 dotted with V2 cross V3. This is one of those things that I expect you can either see immediately or be able to deduce if I gave you a couple minutes just to write things down. Okay, it's V1 dotted with V2 cross V3. What is that? That's V1 dotted with plus or minus V1, right? V2 cross V3 is either positive V1 or it's negative V1, because these are orthonormal bases. And so you either get plus or minus V1 out of that. Okay, but rotation by around some axis by some angle theta has, well, it's got eigenvalues. What are the eigenvalues of a rotation about some axis in R3? All the eigenvalues. Just think of it, right? So rotation, what does it do? There's this line, and that line is fixed. What can you tell me about the eigenvalue there? It's 1, so rotation has eigenvalues of 1. And what can you tell me about the eigenvalues of rotation in a plane? Ben already said it, actually.
They're complex.
They're complex. The complex conjugates of one another. Okay. They're 1 lambda and lambda bar, right? For some lambda complex number. What can you tell me about this complex number? What's the length of lambda? It's 1. Why is that? Well, this is lambda times lambda bar. Nicole, why did you say it was 1?
Things.
Say it again?
You're not stretching things, you're just rotating them.
You're not stretching, you're just rotating. So lambda bar is 1. Okay? So you've got this length equaling 1. So then what? What's the determinant of this thing? What's the determinant in terms of the eigenvalues? It is the product. And that's 1. Right? So what we get out of that is that V1 dot with plus or minus V1 is equal to 1, and that implies that you have the positive sign. Right? We're taking V1 dot plus or minus V1, so V1 dot minus V1 is minus 1, so it has to be V1 dot plus V1. That's all. Okay, so that was it. So we just showed that every orientation preserving isometry of the sphere is rotation. So every isometry of a sphere is rotation followed by a reflection. Or if you like, you can literally say it as, if it's orientation preserving, then it is just rotation. If it's orientation reversing, then you can literally flip the sphere upside down and then do a second rotation. It doesn't have to be followed by some random reflection. It can be any fixed reflection that you like, and then do a rotation that gets you where you need to go, because at that point it's orientation preserving again. Okay? Linear algebra and geometry. Good. Questions about that? Yeah, Ben.
You can't really have rotation around an axis if you're in R2, for example, right?
Well, what do you mean by an axis?
Looking at it, a fixed line. Yeah.
So you said fixed line. So what is an axis for you? This is an important point, because when you make 3 into n, right? If you make 3 into 2, then you have to say what you mean by an axis. And then if you make 3 into 8, 36, or 277, then what's an axis? So what do you mean by an axis? We actually did this in 221. In your version of 221, we actually did this. We mentioned it. I don't know how briefly. I'm not sure whether we did it in the other versions of 221. An axis for a rotation has to be a subspace. An axis for a rotation of a real vector space is a subspace of codimension 2. So inside of R2, an axis is going to be the origin. And inside of a space of dimension 277, it's going to be a space of dimension 275. The reason why you want that is because the orthogonal complement to a subspace of dimension 275 is a subspace of dimension 2. And in there, you can do a rotation. Fair enough? Yeah, so we want our so when I say rotation around an axis, what I really mean is there's a subspace of codimension 2, and I'm rotating the complementary two-dimensional subspace while fixing the codimension 2 subspace. Further questions?
So.
Yeah.
Wouldn't we have a nice, for the general case for in dimension n, wouldn't we have an isometry for by selecting any subspace of dimension, any subspace, and making its complement going to the opposite, like to negative?
Yes. Yes, that's right.
So
what you're saying is basically if you take an identity matrix and throw on any number of minus signs, it's an isometry. That's true.
yeah, so
Up to change of basis, they all look like that, right?
yeah.
Yeah.
So how does this relate to our conclusion that everything is a rotation?
So in R4 or more, it's not enough. You can't, it's at least one is plus or minus 1, right? It has a real eigenvalue. In R4, for instance, it doesn't have to have any real eigenvalues. So there might be a rotation around this axis and a rotation around this axis independently. So there's sort of like multi-rotations. Because there's 4 dimensions, so you can rotate these 2 dimensions and rotate these 2 dimensions. And more or less, that's what all of these things look like. They kind of look like multi-rotations about collections of axes.
So our conclusion would generalize into the composition of a few rotations.
Yes, around sort of independent or orthogonal directions, and then translations and so on. Yeah, more or less, that's what they feel like. Yeah. Others? Yeah.
In that 221, we talked a little bit about the concept of signed area. That's the same as
Of what?
Of signed area, like
Signed area, yes.
like the determinant of a linear transformation is the signed area of what's sort of distorted.
Of the image of the standard basis vectors. Yes, that's right.
So having negative signed area is the same as having a negative orientation, right?
Yes, so if you have a negative signed area, what it means is it does something to the actual area, but it also reverses orientation. So the sign is just sort of a separate thing that tells you about what happened to the orientation. And then the area is the area. Yeah. Yeah. Good. So just as an aside, so other symmetry groups. You can ask to preserve things like preserve it. So you can ask for, okay, you can ask for rotation. And you can think of this as going to be R, or the complex numbers, or the Hamilton quaternions. And raise your hand if you've seen Hamilton quaternions. Yeah, okay. So you can rotate those two. And those are what, those preserve things like distance or angle, right? That's what these groups preserve. You can think about preserving scaling. Sorry, not preserve. You can think about scaling as the group, right? So then that would be something like R or C, or in fact, arbitrary field F, right? You can scale in any field. It makes sense to do scaling, right? Rotation really only makes sense when you have sort of an underlying real structure. You can think about translation. These are symmetry groups. You can think about affine or projective transformations. And what I mean by that is I'm going to draw a projective transformation for you. So if you have, let's say, a line that looks like this, and you've got 4 points that look like that, then you could imagine that you have an observer who's taking a picture, that's supposed to be an eye, who's taking a picture of these things. But the question is, where's their film? Right, so their film is likely to be, let's say something that looks like this. So there's their film. So what they're doing is they're looking at those 4 points, and what's happening is each of these things has an image on that film. So you're going to draw a line there to there, there to there, there to there, there to there, and then you get those 4 points there. So the map that goes from these up to those, that's a projective transformation. Yeah? So you can look at groups of these things. Why are these kinds of things useful? I mean, these transformations preserve various kinds of things, right? Even scaling preserves something. What does scaling preserve, if you think about this? Yeah.
Sort of direction, unless you scale by negative.
It preserves direction, it preserves shape, right? I mean, if I had something that looked like, here's my amoeba or something like that, right? I'm looking at this amoeba at 50 times magnification. If I looked at it at 100 times magnification, it would still look like this. It would just be twice as big. But I'm not interested in how big it is. I'm interested in the shape that I have over here. That's particularly true with things like faces. So this has applications to things like, so I'll just say computer vision, rendering, 3D imagery construction. So how do you do 3D imagery construction? What you have is essentially a bunch of these, right? You've got one fixed three-dimensional thing, and you've got a bunch of projections onto planes, and you want to reconstruct the three-dimensional thing. So you need to know about projective transformations to do the reconstruction of this three-dimensional thing from all the two-dimensional images of it. You could be interested in facial recognition, morphometrics. Morphometrics is these shape-like things where essentially what you do is you'll put a bunch of landmarks on it, and then you say, well, these landmarks are just points in the plane. You list them all, but you only care about them, say, up to scaling and translation, right? Because if you'd move the slide a little bit, it's still the same thing, or if you zoomed in a little bit, it's still the same thing. This happens if you're actually taking pictures of things and you don't have a fixed microscope when you're taking with a camera. If I stand here, if I stand there, I want to say that I ended up with the same picture of this, so it got a little bigger when I went closer, but that's not a big deal. So for face recognition, what happens with face recognition is you've got a bunch of landmarks on the face. That's your matrix A, right? So these things are all the landmarks. And these would be, for facial recognition, you'd have these things in R3, so they'd be actual points in R3, or maybe they'd be points in R2 up to projective transformation or something like that, right? Because every picture of a face, if you do a picture of a face and you do a projective transformation, it's now just a picture of the same face, but from a different angle. Well, I want to say that it's the same face, it's the same data point, right? So I say that this is going to be an R to the N by D. So that's N, that's D. So I have D points, and what does D stand for? D stands for data, right? So I'm going to say that A is going to be equivalent to A prime. That's if these are the same data point, if A prime is equal to G times A, where G is an element in this group, right? So I just want to say that, it's the same face. If you have a picture of a face here or a picture of the face there, I want to say it's the same data point if this image is off by a projective transformation from this image. And that's why it's useful to understand these groups. And then the whole point is that X is going to be R to the N by D modulo the action of G. Or do you want to know what's the set of faces? Well, you take landmarks, one on the nose, one on each eye, one on the chin, and so on. You take these matrices, and you say that two of them are equivalent if they're off by multiplication by some group element. Then you're going to take the space of matrices, and you're going to mod out by the group G, in the same way that we did for the Grassmannian and the flag drawing. And the point is that this is a variety. This is an algebraic variety. It's also a metric space. You can make it into a metric space. It isn't naturally a metric space, but you can make it into a metric space by saying that the distance between, let's say, the class of A and the class of B is going to be something from linear algebra. And you could choose, depending on the application, you can fix what that distance is using the fact that these things came from matrices in some way. That's how this stuff gets used in real life. These are all genuine applications of linear algebra. That's the end of the aside. I just wanted to indicate that what we're doing is quite general and quite useful. And there's sort of, if you're thinking about your term paper, then any of these things, I didn't write them down there, but they're listed here. Computer graphics or, imagery construction. We'll say more about, sort of physics-y type stuff. So we're going to do Lie groups a little later, and that's going to be more about quantum mechanics and stuff. That's why we introduced manifolds and groups, so that we can do Lie groups. Okay. So for the moment, let's bridge into unitary groups, which is going to be complex numbers. So now we're going to let, so whenever I write this boldface F, I'm always going to mean, in this course, R or C. If I don't put a subscript. If I put a subscript, then it's the field of some number of elements or something. But I want to stop saying real or complex. That's what the little blackboard bold thing is supposed to indicate. And let's suppose that we have the standard inner product, the standard Hermitian inner product, standard Hermitian form, and that's going to be on F to the n. Okay, so I have a little note to myself. This stands for the following are equivalent. And on a blackboard during a lecture, that's fine. But in tech, it takes so little time to write the following are equivalent. If you want, you can define a macro, which says \TFAE, and it will write out the following are equivalent. But if you're writing in tech, you should just write the words. There's no reason why this should ever appear in print. It's a shorthand device, that's the idea. So this is actually, there's no colon, it's a period. The following are equivalent, the sentence. 1. If I take XA and pair it with YA, then that's going to be equal to XY for all rows XY in F to the n. So I'm thinking of them as row vectors. And then the definition here is that A lies in O sub n sub F. All right, so for reals, we already saw this. The point is you can do this for complexes too. 2, right multiplication. Rho sub A, the rho stands for right, the Greek letter R, right? Preserves orthonormal bases. By which I mean is that V1 up through Vn orthonormal implies that V1A up through Vna is also orthonormal. And remember, the point of this proposition is that these things are equivalent. So while I'm writing this down, let me tell you, I am not going to prove this for you. But we can talk about it after I'm done writing it down. But these sorts of things, you should use your knowledge of 221 stuff to prove these things. So 3 rows of A are an orthonormal basis of f to the n. I have to say a basis of f to the n because I want there to be n rows. Or A star is equal to the identity matrix. The columns of A are an orthonormal basis of f to the n. I'll just call, and I'll say row. So proof, again, this is an exercise. And it's not assigned. I didn't assign it. But there it is. Some of these things are pretty easy. So think about 4 and 3, for instance. Right? So you're just going to interpret the multiplication of A with A star to be the inner products of the various rows of A with themselves. Right? Because if you take a row of A and a column of A star, that's the inner product of the corresponding row of A with the corresponding other row of A. Right? Again, the product of the ith row of A and the jth column of A star is the inner product of the ith row of A and the jth row of A. And the same thing for 4 and 5. Right? It's just interpreting matrix multiplication in the appropriate way. Let's see now, XA, YA. So this is the definition. But so what is the inner product of XA and YA? By definition, it is YA star times XA. Right? Or maybe it's the other way around. Maybe it's YA times XA star. Right? The point is just going to be YA, A star, X. And there's that A star that's going. Yeah. These things, I could write down the proof, but so could you. And so it's not worth our time to actually have me do it. I just want to make one last definition. The definition is that UN is O n of C. This is called the unitary group. So today we did a study of ON of R. So we kind of know what ON of R feels like. The next time we're going to do a study of what UN feels like. UN is an extremely important group. It is the foundation of quantum computing. It's the foundation of all sorts of physicsy type stuff. There's all sorts of geometry that comes out of UN.